In section 13.3, we learned about how to take derivatives of multivariable functions, which we called partial derivatives. We would like to expand upon that topic by talking about how to take derivatives of composite functions, which brings us to the chain rule. So to begin here, we have the chain rule for derivatives. First, we're going to suppose that we have component functions x of t and y of t that are differentiable at t. I want to emphasize here that these are single variable component functions. And then let's suppose that z is a multivariable function expressed by f of x, y. Suppose that it's differentiable at the point x of t, y of t. Then we can find that derivative of the composite function z of x of t and y of t in the following way. We say that the derivative of z with respect to t, and I want to emphasize here that these are standard d's and not the partial d's because this becomes a single variable function, is equal to the partial of z with respect to x times the derivative of x with respect to t. So I'm circling these things because I want to call out that half the time we're taking partial derivatives because we're working with a multivariable function. The other half of the time we're taking standard derivatives of one variable functions as in Calc 1. So we take the derivative of z with respect to x, multiply it by the derivative of x with respect to t, and then same thing here for the y variable. Now again, the Leibniz notation in this sense is really useful because although we don't actually do this, what you can do is you can think of kind of canceling out the del x and the dx, and the same with the y's, and it leaves you with just the z's and t's on top and bottom. So again, that's just more of a way to help you remember how to set up your chain rule. You run through every possible derivative of the z variable and then multiply by the corresponding standard first derivative. Now, this chain rule is written out assuming that your function f is in terms of two variables, x and y. However, this can be expanded to a function of three variables with x, y, and z. And you'll notice the only change here, of course, we now have w representing our function, but we also have this third summand here, which just includes the partials with respect to z, but it's otherwise the exact same setup. I want to urge you to not memorize this formula. Rather than memorizing, just remember that you need to run through every possible partial derivative of the multivariable function, and then you just need to multiply each of those partials by the corresponding single variable derivative. All right, so let's go into an example here. Depending on the set of the function, either find dz dt or dw dt. So for number 4, we're going to look at dz dt. All right, what I like to do is I like to just write out my chain rule first of all. So I'm not even going to look up above at the top page of the notes here. Let's just write it out. I'm going to say that dz dt. First of all, I know that z is a function of two variables, x and y. So I need to run through those partials. I'll go through partial z, partial x. But I want my final answer in terms of t, not x. So I'm going to multiply by dx dt. And then I need to run through the other variable, partial z, partial y times dy dt. And now let's just start plugging in all of these various terms, starting with partial z, partial x. Remember, you can rewrite z as 1 plus x minus 2xy to the 4th to the 1/2 power. And so thinking of it that in that way, when I pull the 1/2 down in front and subtract, it's going to push that square root to the denominator. So what I'm going to have is a 2 square root of 1 plus x minus 2xy to the 4th. And then the chain rule will have me multiply by the derivative of the inside with respect to x. So that's going to give me a 1 minus 2y to the 4th. All right, so this expression is del z del x. Now I need to look at my x of t function and take its derivative. So the derivative of the natural log of t is 1 over t. And now I'm going to move on to the second part of my summand. I'm going to take del z del y. So again, my denominator is going to be exactly the same. I pull my 1/2 down in front, leave everything on the inside, And then when I subtract 1 from the exponent, it becomes a negative 1/2, which is pushing it down to the bottom. And then the derivative of the inside this time with respect to y is a negative 8xy cubed. And then finally, I need to multiply by dy dt, which is just 1. So I'll indicate that right there. Now, if you stopped at this point, I would give you partial credit, but not full credit. And the reason is because we want our final answer to be in terms of t. There, I just highlighted that t. And right now I see x's, y's, and t's. So now what you need to do is go back up to your component functions. Wherever you see an x, replace it with natural log t, and wherever you see a y, replace it with t. All right, so let's see what we get here. I'm going to just factor out this common factor, which is a 1/2 square root of 1 plus my x is going to become a natural log t. And then I have minus 2. Y is t, so I'm going to write it as t to the 4th natural log t. All right, this is my common factor. And then what's left over here? So what I have in my first summand is all of this expression that I just circled in red. So that becomes a 1 minus 2t to the 4th over t. And now for the other expression, I'm left with just this numerator. And so that becomes a minus 8t cubed natural log of t. All right, and now that I have gotten rid of all of my x's and y's, and the only variable I have in here is a t, that tells me that I am finished with this problem. All right, so there is my dz dt. Okay. So moving on to 8, same thing. This time we have a function of 3 variables and we want to find the derivative of w with respect to t. So we're looking for dw dt. Again, let's just run through the chain rule. W is a function of 3 variables, so I need to take the derivative of w with respect to x, y, and z. So I have del w del x. And then I need to get that back in terms of t, so multiply by dx dt. And now move on to the next variable, del w del y times dy dt, and del w del z times dz dt. All right, and like I said, I will write this chain rule out every single time I do it because it's my roadmap. I'm going to just follow this now and plug in all of the appropriate derivatives throughout. So next, I want to take the derivative of w, but with respect to x. So the outer function is a natural log. That's going to push everything to the denominator, 1 over the inside. So 3x squared minus 2y plus 4z cubed. And then on top, the chain rule will have me take the derivative of the inside, but again, this is with respect to x. So I get a 6x on top and the negative 2y and the positive 4z cubed to go to 0. And now let's multiply by the derivative of x with respect to t, which is going to be a 1/2 t to the negative 1/2. So this is my first term. Let's add on my next term, partial of w with respect to y. My denominator is going to be the same. The derivative of the inside with respect to y is just a negative 2. So I have minus 2, whoops, I don't need a square root, over 3x squared minus 2y plus 4z cubed. And then I need to multiply by the derivative of the y component function, which is a 2/3 t to the negative 1/3. And then finally, I need to add on here partial with respect to z, which is going to give me a 12z squared over 3x squared minus 2y plus 4z cubed. And the derivative of z is a negative 2t to the negative 3rd. Now here again, This expression that I have written down has x's, y's, z's, and t's. I want this all in terms of t's. So I'm looking back up to these three component functions and plugging those in everywhere for x, y, and z. So again, what I'd like to do is I'd like to just factor out the common factor, and then we'll go ahead and plug everything in. The first thing I'll do, and I'm going to just grab a different color here, let's go ahead and transform this denominator. So we have 3x squared minus 2y plus 4z cubed. And what is that in terms of t? Well, an x squared is just t. And then plug in for y. And then z cubed is going to be 4z to the negative, excuse me, not z, 4t to the negative 6. All right, so this is going to be my common denominator. Let me go ahead and just pull that out front. So I have 1 over 3t minus 2t to the 2/3 plus 4t to the negative 6. And then let's just see what's left over. So my 6x is going to become a 6t to the 1/2. But notice that this term right here is a 2t to the 1/2 on bottom. So we'll have some simplification there. Next, I have a minus 4 over 3t to the 1/3. And there's nothing I need to plug in there. And then finally, I have a minus 24. Z squared is going to be a t to the negative 4th. And then we have times a t to the negative 3rd. At this point, I would give you full credit for this answer. However, we certainly could simplify. This whole fraction goes to 3. This one's fine. And then these two can combine to a t to the negative 7th. So again, this is optional, but if you wanted, you could write your final answer as 1 over 3t minus 2t to the 2/3 plus 4t to the negative 6 times 3 minus 4 over 3t to the 1/3 minus 24 over t to the 7th. All right, and here is our final answer at this point. All right. So again, these problems were specific to the case where the function was multivariable, but the individual component functions were single variable. So we were seeing in there a mixture of standard first order derivatives and partial derivatives. This next chain rule is the chain rule for partial derivatives. The difference here is that our component functions, which are still being expressed as x and y, are now functions of two variables. So instead of taking a standard derivative in terms of one variable, now we're going to have partials mixed with the other partials. So what we want to do is we want to take the partial of z, which is a function f in terms of x and y, but both x and y are in terms of u and v. So because of that, there is actually two different derivatives we can find: the partial of z with respect to u and the partial of z with respect to v. But you'll notice that this chain rule is very similar to the previous chain rule. We want to go through all of the different variables in z, in this case x and y. And then again, this nice Leibniz notation, we want to take then the partial of x with respect to u and same with y, right? So we have this notation that leads us to this partial z, partial u. And then we have the same thing in terms of v, where now we have v's here for our partials of our component functions. So following very similar here, but again, notice that there are no d's involved. All of these things are del operators because all of them are the partial derivatives. And then at the end of this here, I'm just expanding to, if you have a function w in terms of 3 variables, then we just want to tack on this extra term here at the end to get all 3 variables involved. So we have a couple of examples working with the chain rule for partial derivatives. Let's take a look here. Starting with 22, we want to find del z del u, and we also want to find del z del v. So let's again kind of set up our roadmap here. Z is the function of both x and y, so I need to run through both of those variables. So let's take the partial of z with respect to x. Then we need to take the partial of x with respect to what? Well, look at what we're looking for. We're looking for the partial with respect to u, so I'll put that on the bottom. And then I need to run through the other variables. So del z del y times del y del u. And now just fill in the blanks. All right, what's the partial of z with respect to x? So we see this cosine x function. When I take its derivative, it gives me a negative sine x. The sine y just comes along. It's considered a constant or a coefficient. And then the partial of x with respect to u is just a single 1. And now let me take the partial of z with respect to y. So now the sine y becomes a cosine y. And the partial of y with respect to u gives me a 2u. Here again, I see x's, y's, and u's floating around. I only want u's or v's in this case. V is okay. And so wherever I see an x or a y, which I'm highlighting, I am now going to plug in those component function expressions. All right, so let's see where we're at. We get a negative sine of u minus v times a sine of u squared plus v squared. And then plus, I'm going to just pull that 2u out in front. And then I have cosine of u minus v, cosine of u squared plus v squared. And I can now box this in as my final answer because all of my x's and y's are gone. And this entire expression or derivative is written in terms of u's and v's. So this was the first thing we were looking for. Now let's find the other partial derivative. We're looking for partial z, partial v. So I have partial z, partial x times partial x, but this time the partial with respect to v, and then same for the y coordinate. All right. So these beginning partials are exactly the same as what we had previously. So I still have a negative sine x, sine y. And now the partial of x with respect to v happens to be a negative 1 in this case. Still have my cosine x, cosine y. And the partial of y with respect to v is a 2v. All right, so where are we at now? Again, I'm going to highlight my x's and y's, and I'm going to replace them with the component functions. Double negative on this first term becomes a positive sine of u minus v times sine of u squared plus v squared. And I'll pull that 2v out in front again, and then I get a cosine of u minus v, cosine of u squared plus v squared. And this is my final answer written in terms of the variables u and v. All right, so not too bad as long as you set up your chain rule and feel comfortable with computing partial derivatives. So let's look at one that's got a little bit more going on here. Now we have 3 component functions instead of 2, and we have a function u that's in terms of 3 different variables, r, s, and t. So let's take a look at partial u, partial x, and I'm just going to make a little note here that we're going to do partial u, partial y on page 3. So don't worry about cramming everything here. If I scroll down, you can see I left some white space here for the second half of the problem. So we'll just work on the partial with respect to x first. So let's set that up here. Partial u, partial x. Okay, so what are we going to do? We're going to recognize that u is a function of 3 variables, r, s, and t. So we need to run through each of those variables and take the derivative of u with respect to them. So I'm just going to go in order as listed. Let's do partial u partial r first, and then I need to multiply by the partial of r with respect to x. Now moving on to the next variable, partial u partial s times the partial of s with respect to x. And again, remember, I'm always choosing this second partial to be with respect to x based on what I'm trying to solve for. Finally, the last variable is t, multiplied by partial t partial x. All right, so something that's interesting in this example is when you take a look at the s function, there are no x's. So because of that, we know that this partial derivative of s with respect to x goes to 0. So this entire term is going to drop out. So I'm not even going to worry about computing those, but let's go ahead and do the other pieces. So the partial of u with respect to r is just an s squared natural log t. And then the partial of r with respect to x is a 2x. I'm going to write a +0 placeholder here just to indicate that I'm not forgetting that step, but we already noted that that goes to 0. And then finally, the partial of u with respect to t, the natural log of t kicks the t on the bottom, and I have r s squared over t times the partial of t with respect to x, which is a y cubed. There again, I want my final answer in terms of x's and y's. So I'll make a note here, make in terms of x and y. And so wherever I see anything other than an x or a y, which I'm highlighting now, I need to resubstitute for those variables. All right, so s squared is going to become 4y plus 1 squared. Natural log of t becomes the natural log of xy cubed. And I still have my 2x out back. And then let's find out what r s squared over t is. So that's x squared times 4y plus 1 squared over x y cubed. And then I still have my y cubed out back here. So we can clean up this second summand. I'll cancel my y cubes. I can also cancel an x on top and bottom. And so what I'm left with here is a 2x times 4y plus 1 squared times the natural log of xy cubed. And this equals x times the quantity 4y plus 1 squared. All right, so this is my simplified partial of u with respect to x. And then as promised, we'll do the other piece on the back side. So looking for the partial of u with respect to y. So to begin, let's go ahead and write out our chain rule. So partial u partial y is the partial of u with respect to r times the partial of r with respect to, in this case, we're now looking at y. And then what is our next variable? That's s. So I want the partial of u with respect to s times partial s partial y, and then we'll end here with t. All right, so let me zoom back out a ways so that we can see our whole problem here. And are any of these partials going to go to 0? So now if you look at the r function, there are no y's in that expression. So here we see the del r del y going to 0. So our first term is going to drop out. The other two component functions both include y, so we'll have to evaluate those. So I'll put my 0 placeholder. So let's find the partial of u with respect to s. That is a 2rs natural log t. And the partial of s with respect to y is a 4. And then the partial of u with respect to t is also going to give me rs squared over t. And then partial of t with respect to y is a 3xy squared. Okay, So again, we want to make in terms of x and y. So eliminate r, s, and t. So looking back up to our component functions, we are going to plug in for r, s, and t. All right. So we have, first of all, my 2 and my 4, I'll write as 8. R is x squared. S is 4y plus 1. And natural log of t becomes the natural log of xy cubed. And then our last fraction here, we want r, which is x squared, s squared, which is going to be a 4y plus 1 quantity squared. And then t is x y cubed times my expression 3xy squared. So as I did before, I'll go ahead and just clean up this second summand. I can cancel out 2 y's on top and bottom, and I can cancel out 1 x on top and bottom. And so for my final answer here, I have 8x squared times 4y plus 1 times the natural log of xy cubed. And then once the dust settles here on this second summand, I'm left with a 3x squared 4y plus 1 squared, all divided by y. All right, and here's my partial of u with respect to y. All right. So we've gotten a fairly good feeling for how to compute the chain rule here with both single variable composition function or component functions and multivariable component functions. This next remark here is really just extending that first chain rule that we talked about, where if your component functions are single variable functions and you have a multivariable function with more than, say, 2 or 3 variables, you can extend that single variable chain rule with as many terms as you need, in this case, out to n different terms. And so we have an example illustrating this. We want to find dw dx. Again, I really just want to call your attention to the notation because it's really important. Those D's there mean that we're taking, our final answer will be in terms of a single variable. If I had del's or partial notation, then I would have multiple variables in my final answer. And the variable that I want in my final answer is x. So let's set this up. If I want to find dw dx, all right, what I need to do is I need to identify the various variables in w. So there happen to be 3. I need to run through all 3 of these. So let's start by taking the partial of w with respect to x, and then I need to take the, not partial, the derivative of x with respect to x. Now in this case, this is just going to be 1. So the derivative of x with respect to itself is just 1. And we don't even have a component function for x. But now let's run through the other variables, partial w partial y times dy dx, and partial w partial z times dz dx. All right, so here's our roadmap. Let's follow it along. First, the partial of w with respect to x gives us a 3y squared z cubed. And again, we just have times 1 there. So now the partial of w with respect to y is 6xy z cubed. And now I want to take the derivative of y with respect to x, which is going to give me a 6x. Finally, we have del w del z gives me a 9xy squared z squared. And finally, dz dx, if you want, you can write this as an x minus 1 to the 1/2. So I'm going to pull the 1/2 down, subtract 1 from the exponent, gives me a 1 over 2 square root of x minus 1, and the chain rule would have me multiply by 1. All right, so here is our first step in following our chain rule. But remember, we want our final answer in terms of x. So let me highlight all of the y's and z's. Oops. And so anywhere where I see a y and a z, I'm going to substitute using those component functions. So what I have here is 3 times 3x squared plus 2 quantity squared. And then I'm going to have x minus 1 to the 3/2 power. I'll combine my coefficients to a 36 and an x squared. Then my y is a 3x squared plus 2. And I have a z cubed again, so that's x minus 1 to the 3/2. And then finally, I have a 9/2 x times 3x squared plus 2 squared. And then I have a x minus 1, but then I also have that x minus 1 to the negative 1/2 power there on the denominator. All right, at this point, I would be perfectly happy with you giving me this for an answer. The back of the book likes to factor and simplify as much as possible. And so I'll go ahead and do that with the understanding that you could stop here, and that would be perfectly fine. All right, so for common factors here, let's look. Certainly, I can pull out 1 3x squared plus 2 from every term. I can also pull out some x minus 1s from every term. And so the question becomes, well, how many can I pull out? Notice that this simplifies to an x minus 1 to the 1/2 power. So it looks like that's going to be as high as I can go. And then as far as coefficients, we have a 3, we have a 36, and we have a 9/2. So I can factor a 3 out front. So let's see what we have here. I'm going to factor a 3, a 3x squared plus 2, and an x minus 1 to the 1/2. And let's see what's left over. We took out this 3, we took out one of these, and we took out one of these. So I'm left with a 3x squared plus 2 times x minus 1. Next term, I took out a 3, so that leaves a 12. This entire 3x squared plus 2 is gone. I do still have my x squared, and I took out 1/2 of these, so I'm left with an x minus 1. And then for the final term, I have 3/2 x. I took out all of the x minus 1s and a single one of the 3x plus 2s. All right, and so I factored out my common factor, and now all I have left to do is to simplify what's inside the brackets. So I'll go ahead and expand this out. I'll scooch over here to make a little bit more room. All right, so I have a 3x cubed minus 3x squared plus 2x minus 2 plus 12x cubed minus 12x squared plus 9/2 x squared plus 3x. And finally, combining like terms, I have 3 times 3x squared plus 2 times the square root of x minus 1 times and I just noticed one slight mistake up above, so I'm going to correct it here in red. There should have been a 2 right here, which would then change this 9/2 squared to a 9/2 cubed. So please do make that correction. So if I add up the cubes, The 3 plus 12 is 15 plus 9 halves. That's 30 halves plus 9 halves for a total of 39 halves, x cubed. And now let's add up the x squared terms. Looks like I only have 2 of those for a total of negative 15x squared. Linear terms, we have 2, so 5x. And then finally, my constant negative 2. So here's the answer that the back of the book would give. I'll box that in. However, as I stated before, I would be perfectly happy with you also circling the answer that we got up above here, which I've kind of marked up at this point, but I'll box it in as well. The unfactored form, but making sure that your final answer is strictly in terms of x's and no y's and z's are involved. All right, we're going to end this section working with implicit differentiation, but I promise you it's not what you think it is. It's actually a shortcut for implicit differentiation. And so what we're working with here is if we have a function where all of the x and y variables are on one side and the right-hand side is just equal to a constant, then we can find the derivative implicitly in a shortcut way. And so you'll notice what it says is that the derivative of y with respect to x is equal to the negative ratio of del f del x over del f del y. Now, this isn't anything magical, all right? So what I'd like to do up here in the margin is just kind of take a look at this. And if I wanted to differentiate this function, so I'll just write diff above to indicate that I'm going to differentiate this. Then what am I going to do here? Well, f is a function of x and y. So I'm going to take the partial of f with respect to x. And then x is single variable, so times the derivative of x with respect to x. And then again, I need to take the partial of f with respect to y times the derivative of y with respect to x. This is just the chain rule. And then on the right-hand side, I'm taking the derivative of a constant, which is 0. And so now if I solve for dy dx, I'm going to kick the one term over. So I'm going to leave del f del y dy dx on the left-hand side and the negative del f del x on the other side. And remember, dx over dx, that's just 1. The derivative of x with respect to itself is 1. And now, of course, you can divide both sides by del f del y, and it gets you down here. So this is not something that's being pulled out of a magician's hat. This is just using the chain rule and the fact that the derivative of a constant is c, and they're just getting you to this point to kind of save you the process of going through that implicit differentiation. A similar equation holds for a function with 3 variables. And in this case now, instead of the dy dx, notice that we have the del notation because now we have more variables flying around. In both of these cases, we're assuming that we're not dividing by 0. So that is the one thing that must hold in order to apply these formulas. So let's go ahead and apply these implicit differentiation formulas. Starting with 44, we have our implicit formula. What's important is that one side is a constant. If it isn't like that, then you need to move it around so that it looks like that. And we want to find dy dx. All right, so I'm going to go ahead and just write out my formula. That's the partial of f with respect to x divided by the partial of f with respect to y, where the left-hand side is being denoted by f. All right, so first let's find the partial with respect to x. So that's going to give me a 1 minus, I'm going to get a 1 over 2 root xy. And then the derivative of the inside with respect to x is going to kick out a y. And that final term just goes to 0. And then on bottom, I have a similar thing happening. I have the partial with respect to y, so I have 0 minus 1 over 2 root x, and this time times x plus 3. All right, I would give you full credit at this point, but it just looks really ugly. right now. So what I'm going to do is I'm going to distribute this negative to the top, first of all. And then I'm also going to just get rid of the complex fractions by multiplying the top and bottom by 2 square root y. 2 square root xy. And so in this case, multiplying by this, I get the following. I get a negative 2 square root xy plus y. And on bottom, I get a negative x plus 6 square root xy. And so here is my derivative dy dx without actually going through the process of the chain rule and implicit differentiation. And so we'll end here with one more example using the same process, but now in this case working with higher dimensions here. So let's start with del z del x. So again, let's write out our formula. That is negative del f del x over del f del z. And let's go ahead and compute those derivatives, assuming that the the left-hand side is f. I'm going to take the partial with respect to x first. The first term just goes to 0. The second term goes to y squared. The third term goes to 0 as well. And I have a minus sign out front. And then on bottom, the partial with respect to z, I get a 1 over 1 plus z plus 0 plus 1. All right, so again, you could leave your answer like this. It looks a little ugly, or you can simplify it by getting rid of that complex fraction, which is what I'll do right now. And so that gives me a minus y squared times 1 plus z on top. And on bottom, it gives me a 1 plus 1 plus z, which I'll just simplify to a 2 plus c. So here's the partial of z with respect to x. And then similarly, we would like to compute the partial of z with respect to y. And so that's going to be negative partial f partial y over partial f partial z. All right, so this becomes partial f partial y is going to be a 0 plus 2xy plus 0. And then the exact same expression on the bottom. 1 over 1 plus z plus 1. Again, I'll simplify the complex fraction. So my denominator is still 2 plus z. And on top, I just get, oops, and I forgot my negative here, a negative 2xy times 1 plus c. All right. So this concludes our notes for 13.5, the chain rule. Up next, we're going to extend the idea of partial derivatives to directional derivatives, and then talk about how they can be useful in various senses, and also introduce what's known as the gradient.